So today is obviously a bit different. Thank you, Adam, for joining us on Zoom. And thank you, for Mackenzie, for being here. Everyone else, hopefully you're watching this a little bit later. But our content is going to be delivered during a lecture this week. The problem, I figure I will give you an explanation. It's not an excuse, even if you wanted it differently. This is the way it's going to be, so whatever. Anyway, last week I wrote several exams, and so I simply did not have the time to get the videos recorded. Lecture notes were prepped and ready to go, just not time to record lectures. It's actually quite possible because last week I gave so many exams, and this week I'm grading. We may be in the same situation next week because I'll be grading this week. I might not have the time to get all of that set up. So I'd also love to have a conversation at the end of next week to see how things have gone delivering content during class in this way. So keep that in mind as well. Hopefully those of you that are not here with me right now, but are watching this on video later, hopefully you're feeling that this is a good use of our time as well. So, all right, we'll go ahead and get started. Well, actually, I guess before we look at content, it's worth mentioning that we're on pace in terms of the schedule. So I'm really happy with where we're at. I don't think that I planned too much extra time at the end of the semester for slowing down further than more than the schedule anyway. So I didn't leave like an open week at the end, I don't think. Some classes I did that because it's just best to do that, but for this class I don't believe I did. So staying on pace is very good for us, very good. That's really what we want to do. So we'll try to keep up with that. The exams have been graded. The graded versions have been emailed back to you. So feel free to take a look at those and let me know if you have any questions. I don't think that there are any significant issues. Probably the most common issue was just trying to understand the difference between a geometric object and its qualities. So for example, angle measurements versus the angle itself, recognizing those distinctions, and then a line versus the length of a line, line segment rather. Okay, so just those couple of designations or a couple of differences, but that was it, and it wasn't significant. It was just the most common one. Okay, so yeah, let's take a look at this. Here we are. Excellent. So we're getting into section 11, which is angles. Some of this we've already seen, so we're revisiting and reintroducing definitions and ideas that we already know. For example, one of those things is convexity. Let me get myself a blue pencil here. So one of those things is convexity. And a set is convex if whenever you have 2 points in the set, the line segment joining them is also in the set. So if you have 2 points, the line segment between them is also contained in the set. That is convex. If the line segment goes outside of the set, then it is non-convex. So we've already seen this, but just a nice reminder / a little bit more formal. And we want this, we want to remember convexity so that way we can give our next axiom, which is the plane separation postulate. And the plane separation postulate is really pretty much just as simple as it sounds. We're separating the plane, and what we're doing is we're separating the plane into 2 disjoint convex sets by a line L. So any line L, every line L, all of them, if you consider the line, you're either on one side of the line or you're on the other. And each of those halves, one side and the other, creates a half plane, no matter which line you're considering. So, awesome. So any line L divides the plane into 2 disjoint convex sets such that if P is in one set and Q is in the other, then the line joining P and Q, line segment PQ, intersects L. Excellent. is. Okay. And then, as I said, you know, every line separates it. You're either on one side or the other side. But this idea of side, same side, different side, hasn't formally been defined. So we actually need to define that as well, because we want to be absolutely explicit about everything. That's part of the axiomatic approach to geometry. I mean, right, that's the approach to any subject, really. You can only build up your knowledge of it by the definitions and what you can conclude from our definitions and axioms. That's it. So if we have a line L, which splits the plane into two halves, as guaranteed by the previous theorem, let's say that we have A and B, two distinct points that do not lie on the line L. Okay, we have one of two situations. Either A and B are on the same side or they're on different sides. They're on the same side of L if and only if it's as simple as you would think it to be. A and B belong to the same half plane. Nothing surprising there. A and B are on different sides if and only if A and B belong to different half planes. Okay, so we have what the same side is, we have what different sides are. And it's as simple as you would think it is. Nice visual representation, right? When they're on the same side, the line joining them also lies on the same side. And when you have them on different sides, the line between them, line segment, crosses the line F. Okay. So we've already also seen what an angle is, but we want to look at the definition again, focusing on some important differences between the previous situation and this situation. And we'll see what that situation is when we look at the angle measurement, okay? So given three non-collinear points, A, B, and C, the angle ABC is the union of two rays. It is the union of the ray, the ray BA and the ray BC. So it is the union of two sets, right? It is just a set of points, and it is the union of two rays which have the same base, called the vertex. Okay. BA and BC are called the sides of the angle. B is called the vertex. For notation, as we saw previously, there are different ways that we can write this. Of course, it is angle ABC or angle CBA, because the order doesn't matter there, right? ABC or CBA. Or when it's not ambiguous, you can simply call it angle B. You can reference an angle by its vertex when there's only one angle that's created at that point. Excellent. So the focus here, non-collinear, that's the focus of this section, right? We want to emphasize that because we are not considering then lines. Okay, so if we have a line with 3 points on it, we don't have it, it's not creating an angle. Okay, so an angle has to be 3 non-collinear points. So we're not considering that situation. So when we bring that idea into the angle measure postulate, the measure of angle ABC is a real number denoted by M of ABC, right, measurement of angle ABC, such that we have that the angle measure is between 0 and 180 degrees. but we're not allowing equality, right? It can't be equal, and it has to be less than. It's not like we can also say, well, then we can also have something greater than 180. No, everything is between 0 and 180 degrees, and that is the big difference. Okay, previously, we were talking about, we were using our knowledge of that there's larger angle measurements than that. But for our purposes at this time, with what we have, there's no such thing as an angle larger or even equal to 180 degrees. Excellent. So two angles are congruent if and only if they have equal measure. Equal measure. So that's not anything too surprising, but what we do want to do is we want to make sure that we have the correct notation for that. So we use the symbol of an equal sign with essentially like a tilde over top of it, and this designates congruence of geometric objects. So if we have congruence of objects, or we do have congruence of objects where we can have equality of numbers. So angle ABC can be congruent to angle DEF, and when they are, the angle measures would be the same, equal to one another. However, an angle cannot be equal to an angle because they are geometric objects, and this is used for comparing numbers. Similarly, congruence is not used to compare numbers, at least not right now in this course, right? We talk about congruence relations in abstract algebra, but that's not what we're focusing on here. So you may notice, let's see here. Oh yeah, of course, there's a lot that's same between lines and angles. Partially the notation so far and the congruence, right? That they're congruent if their measures are the same. So they're pretty similar so far, and it actually continues to be that way. Even axiom 7 and axiom 8 and theorem 11.6 are all right. They have similar forms when it comes to lines. So there are connections between lines and angles, and you'll see that throughout many of these axioms, theorems, and definitions. All right. So given a line AB and an angle measure theta between 0 and 180 degrees, on either side of AB, there is a point P such that, let's see here, we have the angle, in particular the measure of angle, well, I don't think it matters, ABP. The measure of the angle is exactly theta. Or measure of angle BAP. Right, which one you call the vertex doesn't really matter. So if you have a line A, B, whichever one you need it to be, you can find. So if you need a particular angle coming off of A, then there is some point P out here that makes it true, okay, or that satisfies that makes this angle exactly have the measure you wanted. And you could do the same thing for B as well. So it doesn't matter, whichever one is desired there. But one difference, let's see here. One thing that is at least a little bit different here for the protractor postulate is that this point can be many different points. There are a lot of different points that satisfy this, whereas the ruler postulate, I believe, gave that there's exactly one point depending on which side you wanted to be on or something of that sort. So There are many different points that would make this true, but all we need is the existence of one typically. So that's good. All right. And before we move on, we're going to make a huge blanket statement. We're going to download, right? We're going to recall, we're going to upload, however you want to call it, a whole bunch of definitions. So adjacent angles, linear pair, supplementary angles, complementary angles, vertical angles, obtuse angles, acute angles, right angles. All of those have the same definitions that were given in section 2. So we can just take those definitions and bring them here into section 11. So at this point, we may consider all of these things defined, so we can use them as needed. Excellent. All right, so let's talk about the interior of an angle. The interior of an angle, this is, you may have asked yourself why we needed to know about splitting a plane in half and saying if points were on the same side of a line or not. And this is where we need that when we define the interior of an angle. So the interior of an angle is the set of points P, right, between the two sides. But how do we say that mathematically? Well, it's a set of points P such that, make sure I get this phrased correctly, A and P are on the same side of the line BC there we go, and so we talked about A and P, now we want C and P. C and P are on the same side of the line BA. So that is, right, if you want to think about back in the day when you looked at, solutions to systems of inequalities, okay, where you would shade regions and then where the overlapping shaded regions were the same, that's what your solution was. Well, so we're taking the collection of points that are on this side of this, right, on this side of that side, that's kind of weird, this line, and then the stuff that's on this side of this line. So it's this stuff here that is the interior, okay? So that just looks like a giant mess of scribbling, so I'm going to get rid of that, but it's everything between. But it is also worth noting that the interior does not include the sides of the angle. Right, it's sometimes you're not sure if a set includes its boundary, if the boundary is in the set or not in the set. And in this case, it's not in the set. So the sides themselves are not part of the interior. Yes. Okay. So angle addition, this this corresponds to the line segment addition. If we have P being in the interior of some angle, much like we have above here, then the measure of angle, right, if we were to split this up, this angle plus that one should equal the whole thing, is all that we're going to say here. So the measure of angle A, BP plus the measure of angle, we'll call it PBC, is equal to the measure of angle ABC. Excellent. So this is a little bit interesting for us. The angle addition postulate requires that we begin with an angle, not that we begin with a pair of angles that have a common side. Okay? We have to begin with the entire thing being an angle. And the biggest reason that is because if we start with two angles that share a common side, we could easily end up with a situation where their sum of the measures exceeds 180 degrees, which means that that final thing isn't actually the angle or an angle. So that's what this situation is here, right? Angle ABC certainly is an angle, and the angle CBD is also certainly an angle. But if we were to add them together, we would get something where we would get this measurement, but that's not the measurement of angle ABD. The measurement of angle ABD is this measurement. So we want to recognize that. So let's, I'll write that out. So the measure of angle ABC plus the measure of angle CBD is equal to 120 degrees plus 90 degrees, which of course is 210 degrees, which is more than the allowed 180. So we have a problem, right? The measure of angle ABD, which is what we want it to be equal to, is only 150 degrees, not 210. So the problem is C does not lie in the interior of angle ABD. All right, the angle interior inequality. This has a corresponding theorem in line segment lengths as well. When we talked about line segment lengths, we had something like AB with P between. The measurement of AP is certainly less than the measurement of AB. And we want to take that same thing here. Let's see, I believe this one is written as this measurement is less than that one. So the measure of angle ABP is strictly less than the measure of angle ABC. For this theorem, we do have the proof given on the next page, and so I'm really happy that I don't have to write it out, not because I don't want to write out all of this, but because I suppose it is because I don't want to write it out. I want to look at it. I don't want to have to write it all out. So, so the proof of this is pretty straightforward, but we have to recognize a couple of things here. So there's a remark given, and I'd like to take a look at that before we look at the proof. So the forward direction is we assume that P is in the interior of ABC, and then we show that the inequality holds. Okay, that's part of the exercises. What we want to do now is we want to assume that the inequality holds and that P is in the interior of ABC. So one of the things that we have to use here is that C is, either we would have one of two situations. Either C is in the interior of ABP or P is in the interior of ABC. So in the case of C is in the interior of ABP, we're saying that P is outside, right? Not in the interior of ABC. So P is either in the interior or not. If it's not, then we can say that C is in the interior of ABP. One of those has to hold true. So we're given that ABP is less than ABC, right? That's our assumption. If we subtract this angle, this measurement from both sides, then we get that this quantity is less than 0. Excellent. All right, now here we assume for a contradiction. So suppose C is in the interior of ABP. That is, P is in the exterior of ABC. Right? This is saying P is in the, well, we don't have that defined for us, so maybe I shouldn't say it that way. P is not in the interior of angle ABC. That's what we're assuming here, which is equivalent to C being in the interior of ABP. If that's the case, then according to the angle addition theorem postulate, we can write the measure of angle ABC plus the measure of angle CBP as the measure of angle ABP. Because it is C that is in the interior of ABP. That's the assumption here. Okay. Subtract the measure of angle ABC. Excellent. That gives us ABP minus ABC, which if we look back at 2 is exactly what we had up there. So we do a substitution. We replace this part with measure of angle CBP, which tells us that the measure of angle CBP is less than 0. Okay, so all we did was a substitution and now have observed that the angle measure is less than 0. First of all, that doesn't make sense because we said that angle measures have to be larger than 0. So it also makes sense to say that there's a contradiction there because that contradicts the definition of angle measurement. However, the angle, well, I suppose that is what we're doing here in line 7. The angle measurement postulate says that it has to be larger than 0. So in 8, we say 6 and 7 contradict each other. That's our clear, explicit statement that there's a contradiction. And then we say, all right, well, what do we conclude since there was a contradiction? Well, in line 9, we say that P is in the interior because we're taking line 3. And if it's not this one, if it's not this situation, if P is not in the interior, then it is in the interior. Okay? So P is in the interior, combining lines 3 and 8. All right. So I think that these proofs can be a little bit hard to look at, and you really have to go back and say, all right, what one is this saying? Because there's a lot of letters there. So feel free to, as you're reading these and looking back over them, and even watching this video, have the text open along with the video, and be looking at this this image here. That should help quite a bit. All right. So moving on to linear pairs and the supplement postulate. So we've talked, I briefly mentioned earlier that there was a little bit of a struggle with the concepts of a geometric object and the characteristics of it. So an angle versus an angle measure, a line segment versus the length of a line segment. And we really want to make sure that we understand these differences. So that extends a little bit further, for example, to the idea of a linear pair. Okay? A linear pair is a visual idea. Supplementary angles is a numerical idea. A linear pair is a pair of angles, right, that form a line, right? The two sides that are non-adjacent, the two non-adjacent sides form a line. That is a linear pair. Whereas supplementary angles, the measurements of the angles add up to 180 degrees. And certainly, when we have a linear pair, they are supplementary. And that's what the supplement postulate says. Two angles that form a linear pair are supplementary. Again, that's not anything new. We saw that back section 2, I believe it was. So that idea is not anything new. However, with us looking at it as more of a rigorous buildup, right, our axiomatic buildup, what we want to recognize is that them being two different ideas means that if we wanted to, for example, observe a linear pair in a proof and then discuss the fact that they are supplementary, we would have to observe that they're a linear pair, observe that they're supplementary, and then we could say what it means for them to be supplementary. It would take 3 steps. But we can replace this with just 1 step using the supplement postulate. Okay? So if they're supplementary, right, we can write that they're supplementary, or we can simply write that their sum is 180 degrees by the supplement postulate, rather than the 3 lines. Okay. So it's okay to use the supplement postulate. Of course it is. Let's give it. Use it. Okay. So this is a key point that you should know and I should know as well. Again, remember that I didn't write this text. So this statement of I will not require you to state that angles form a linear pair in a proof, I will hold to that because it's here in our text, or I'll do my best to. So as it says, when you see a linear pair, you can simply say that they're supplementary, or that you can say that their sum of the measures is 180 degrees, and that's fine. All right, angle bisector. This is analogous to the midpoint of a line segment. So if we have a point D in the interior of ABC, the ray BD is a bisector of the angle ABC if and only if. So we're going to use, similar to what we did in the statement about the midpoint theorem, we're going to give a little bit more, or in the definition rather, we're going to give a little bit more than what's necessary. So that way we can use the definition conveniently in our proofs. So if we have, it's the bisector if the measure of angle, let's see, ABD is equal to the measure of angle DBC, or CBD, whatever you want to say there. Right, this is sufficient to define angle bisector, but we'll take it 1 step further and say that this is 1/2 of the measure of the angle ABC. So we could take this, give myself a little extra room here, and just try to emphasize with a nice visual representation. So let's say I have A, B, C. Then D, if we take this point D, and the angle ABD and DBC, if those are equal, then we would say that this ray, BD, is an angle bisector. Okay, nothing too surprising there. Okay, we're cruising along really well right now. Is there anyone that would like me to pause for a moment? Any questions? Any concerns? All right, cool. So we just have a few additional theorems to look at. All of the proofs of these are in the exercises, and they're all pretty straightforward. And I'm happy to give out hints, so I'm going to do that as well. So angle bisector existence. Every angle has exactly one bisector. Now, I haven't gone through the proof of this, but a lot of times when you're looking at uniqueness, the best way to prove uniqueness is to assume that it's not unique and then come up with a contradiction. So a lot of times that's the case, and so that's what I would suspect for this one. You could prove it by contradiction, assume not unique. Okay. The supplement theorem. If two angles are supplementary to the same angle or a pair of congruent angles, then they are congruent. Let's see here. My recommendation would be to use, so you can use, since it has same angle or to a pair of congruent angles. I'm trying to remember if there's any issue with saying an angle is congruent to itself. I don't believe so. I believe you can say an angle is congruent to itself. So if you prove it for congruent angles, then you've proved it for same angle. And essentially just use the definition of supplementary angles. And as long as you do that, right, you have some equalities that allow you to make some substitutions, and doing that, it all falls right out. All of these proofs are extremely short. Based on how a lot of you guys write proofs, so whether that's I'm talking to the 4 people that are registered this semester or the multitude that will be registered in the future, so far one concern that I have about student proofs is that you like to write them in a very small amount of space. Not that you need to say more than you do, but feel free to space things out a little bit. More white space makes things easier to read. That's absolutely true. So, I feel like if you guys wrote these normally, you could fit 4 of them on a page without a problem. I would probably write 1 on a page, but it might only take half a page. Anyway, the complement theorem. This is exactly the same as the supplement theorem, except for complements. So if 2 angles are complementary to the same angle or to a pair of congruent angles, then the 2 angles, are congruent. And the proof should look almost exactly the same, except you'd have 2 angles, the measurement of 2 angles adding to 90 degrees instead of 180. All right. If D is in the interior of ABC, a right angle, then ABD and DBC are complementary. I believe that's just by definition. So there's like 2 lines to write. If you're not following along, right, if we have an angle that measures 90 degrees, D is out here somewhere, then this angle and that angle add up to 90 degrees. All right. Vertical angle theorem. Vertical angles are congruent. And all you have to do to prove this is to make sure that somewhere in your proof you cite the supplement theorem. Okay. the supplement theorem immediately, or almost immediately, gives the vertical angle theorem. I suppose, much like any proof, there's multiple ways to do them. So if you don't cite the supplement theorem, you may have found a different way to do it. That's fine, but that would certainly be one way to go about it, and it would be short. All right, beyond that, that's it for the section. So everything beyond that is just the exercises. So thank you for your time and your attention on this section. I'm going to go ahead and stop this recording because we're done with the section.